Okay, welcome, and what we will discuss today is this sub-block interleaver. Just to recall, we have been discussing this 5G PDCCH chain, okay, physical downlink control channel, and this is the agenda for today. We will discuss this sub-block interleaver first, and hopefully we'll start discussing the rate matching principles for PDCCH. Okay, these are the references, but before we get into this sub-block interleaver, let's recall what we have done till now in some form. So this is basically our PDCCH transmit chain, okay, and what we get is this DCI, which is maximum length 140 bits in the downlink, okay. So CRC is appended, 24 bit CRC is appended, and there is this CRC scrambling, okay, which is required because UEs do blind decoding to find out whether their DCI has been transmitted or not. Okay. The rest of the chain is basically designed to facilitate these early decoding, like blind decoding attempts. Okay. And we saw an example of this CRC interleaver plus CRC interleaver, how is it designed such that it can facilitate early decoding. Okay. Right, and we learned some ideas about polar encoding also. Only a little bit which is required for us to understand how the rest of the chain is actually designed around it. And then we are going to focus on this sub-block interleaver. Then there is this rate matcher, then scrambler, then 4-QAM modulation. Okay, right. So these modules we understand to a certain extent, to actually a good extent, because we have seen PDCCH chain, but we'll see how it works. There are subtle differences, okay, and the rest of the receiver chain does just opposite of that. Okay, so what is the CRC interleaver? Just to recap, it is designed to facilitate early termination of polar decoding. We'll not go into the details of it. We have seen it already, and it is designed to interleave maximum 164 bits. Okay, because the maximum payload is 140 bits, DCI payload is 140 bits, and then 24 bit of CRC. Okay, so it is designed to facilitate that. And if you remember, there is this mother CRC interleaving pattern, okay, which is of 164 bit. Okay, and all interleaver pattern for lower k values, okay, they are derived from it. Okay, so it's only that this 164 bit pattern is stored, and after this with little bit of processing, one can derive this other lower length pattern from it. We saw that. We took an example and we derived that also. Okay. So our focus, as I said, is going to be on this sub-block interleaver now. Okay, and how is an interleaver? That's all it is. Idea is it will again shuffle the bits. Okay, how does it do? That's what I'm going to show you. Okay. So just to begin with, that sub-block interleaver basically takes input from polar encoding. Okay, the output of polar encoder has to be shuffled again. So the bit output from this polar encoder is denoted as this. Okay, D0 to Dn-1. We remember that the output of the encoder has length n. Okay, and there is a restriction on this length n also, and we will calculate this. How this n is basically, how does this n depend on the number of resources allocated and other parameters. We are going to do that also today. Okay. What we are focusing here is that the output of polar encoder goes to the sub-block interleaver. Okay. And this becomes the input to the sub-block interleaver. Okay. And let's see how this sub-block interleaver is designed. Okay. So what is this? If you look at where this sub-block interleaver is coming, it is coming between polar encoder and the rate matcher. That's what I am saying here. Okay. If you look at the next bullet, so these polar encoded bits are interleaved before rate matching. Okay, and how is it designed? That's the key idea. Okay, that the sub-block interleaver ensures most important coded bits are retained during rate matching. Okay, and why I am saying so, because we have seen this earlier, that the polar encoder design fundamentals are such that each of its encoded bit has a different reliability. Right? Okay, and if the interleaver is poorly designed, then it will shuffle the bits such that it will shuffle the bits, and when the rate matching happens, then the rate matching will drop some of these or most of those high priority bits. Okay, right? So you see this, there is a constraint. Okay, because there is a polar encoder, then all the bits do not have the same reliability. correct? And anyway, there is a rate matcher, and we understand what rate matching is going to do. Okay, it's going to match the lower rate code or a rate 1 by 8 code, that's a mother code rate, to the rate which is actually asked by the user. Okay, so it is going to drop certain bits also, right, depending on the rate which is asked by the user. Okay, so keeping this in mind, the sub-block interleaver ensures that most important coded bits are retained during the rate matching. Okay, and how is it done? That's okay. So this is basically, if you see this, these are the bits which are basically goes as an input, and these are the bits which come as output. One thing you will see is this basically, what am I showing here, that what is the block I am considering. It is if this is hidden, but this basically this 32 length block I am considering. Okay, so the interleaver is designed to interleave only 32 bits at a time. Okay, so that's what is happening. Okay, so you see this, some of these bits are just coming out as such, but some of these bits are like interleaved, but the key thing is here is that it's only 32 bits are being considered. Okay, and it is designed such that most important bits are retained. Okay, so what does this bit interleaver do? Okay, interleaver divides the n encoded bits. How many bits we have? Okay, total of n, capital N. That's the polar encoder output, right? And what is it doing? Remember this notation, capital B. Okay, so what is it doing? It basically divides this into how many streams? You see n by 32. Right? If n is 32, then how many streams will be there? Only one stream will be there. And of course, depending on like the length of this interleaver, depending on n, we'll get different streams. Okay, point number 1. Okay, that's how it interleaves, and interleaves according to a list of 32 integers. Okay, and then what do you have? You have 32 bit values. You have to interleave, and you need those. Where should these bits be written? You need that sequence, right? Okay, that's how, and that sequence is called P. Okay, right? That's what is happening. Okay, and then based on that, you get this interleaved vector y. That's what is written over here. D is the input, y is the output, and what is the input length and what is the output length for the interleaver? 32. Okay, and whatever it does for one stream, it is going to do the same thing for the other stream also. Do you get it? What we are saying here? Okay, so it interleaves 32 bit at a time. Fine. Okay, it's going to break that n length sequence into how many streams? B. Okay, right? So whatever we are saying here, this is how it happens in the standard. Okay, that bit interleaver to a sub block interleaver. What is this? This is the output of the polar encoder, so it becomes input to the sub block interleaver. Okay, and then bit output of the interleaver is decoded as y. I just showed you. Okay, D is the input, y is the output, and length remains the same. Okay, right? And now just for example, okay, that if n is 32, polar encoder length is 32, what will be B? B will be 1. Correct? Okay. Now that's how it is given in the standard. That's how standard does it. Okay. You see this index is running from 0 to 31 because you have to interleave 32 bits. Okay. And then what happens after that? Okay. You look at this index. What is happening here? This is floor. Okay. 32 n by n. Okay. So what is this? What have I written here? What is 32 by n? 32 by n is 1 by b. Right? Okay. B is n by 32. Okay. So 1 by b. That's what I am writing over here. Okay. Correct? And then n by b. So then what happens? Okay. What is b? 1 here. Okay. And n by 1 floor of that you're going to get n. I'm just simplifying this formula for you. Okay. There is another index which is running from 32 n by b. Okay. Like this index value is this. Okay. And what happens in this case? It will run from it is equal to n. Okay. Right. Now see this. Okay. So what is happening here? Based on this indices which are given to us, P, that interleaver sequence is given to us. Okay. Right. So what now? This is the index. Okay. Final index which is being calculated. This is given to us. Okay. Now Pi into B plus this. Okay. This is a formula which is according to which we are going to interleave. Okay. So how does this simplify in this case? That's what we are trying to understand. Okay. So what is this? P of I is some sequence which is 32 length sequence which is given to us. We are multiplying it by B. what is happening here, that's what we'll understand, but plus mod of n comma b, okay. B is what? 1. Mod of any integer comma 1, what will you get? 0, right, okay. So what are you left with? Pi into b, b is 1, you get p of I. What will happen if n changes? Okay, you need larger number of indices, that's what is going to generate for you, that's all, okay. So this is again, what is happening, only 32-bit pattern is defined, okay, and as I said that this interleaver operates on only 32 bits at a time, but what about next 32 bits? It will do the same operation, but the indices are generated accordingly, that's all, okay. It will get multiplied, right, you see this p of I plus into b, what will happen? Indices are are doubling, right, and then according to that whether n is even or odd, okay, 0 or 1, it will take that value. So suitable indices will be generated for higher length sequence, that's what this is doing. You can do it for yourself, n is equal to 60, if it is 64, b becomes 2, and accordingly suitable indices are going to get generated, okay. And this is the interleaver pattern, that's all, okay. So here the mother interleaver pattern is 32, okay, right, and from there all other indices are being generated, okay, right. We don't call that as mother in this case, because what happens is you derive from it, you derive shorter sequences from it, okay, right. But here we are extending it, okay, kid is smaller than mother, that's what it is, okay, but here we are like enhancing it, so we don't call that mother pattern, okay. So now you see this, what is happening, you take this sequence D, right, but this is, you will read this from this sequence and write it at this sequence, correct, okay. What is j of n? N is equal to 0, okay, j is another sequence you have gotten, okay, and what is in this case, for our simplified case, what is this? It comes out to be p of I, that's the pattern given to us, correct, okay. And if n is 0, you will take p of 0, in some index, let's say it is 1, okay, so you will take d of 1 and write it at y of 0, right, okay. And if you go back and see, so what is happening, so you will see that j of 0 is actually 0, because you saw that first 3 bits were going as such, right, okay. So j of 1 will also come out to be 1, j of 2 will also come out to be 1, j of 3 comes out to be 4, j of 4 comes out to be 3, okay, right. So that's what it is, you see this 0, 1, 2, 0, p of 0, this is p of 0, right, because j of n is becoming p of n, and for if you take I as 0, what is happening? I is, where is, okay, I is equal to n, right, if n is 0, I becomes 0 in this case, okay. So p of 0 is 0, right, and n is also 0, so 0th bit is going to 0th position, okay, right, that's how this interleaving is happening, and this is the pattern which is defined for us. What is this? What am I showing you? This is this pattern, p of I. That's what I said, 32-bit pattern is defined for us, okay, and from there you derive j of n, which is like extended pattern, but in this case, because n is 32, j of n for this simplified case, it becomes same as p of I, right, okay, and that's what is being written, and you can check that, okay, right, and for first 3 bit we saw that 0 of 0 goes to 0, 1 goes to 1, 2 goes to 2, 4 goes to 3, 3 goes to 4, that's what I said, 5 goes to 5, and 6 goes to 6. That's the pattern, okay. And similarly, you can do this operation for higher n also, okay. And what is happening at the end of the day, that these bits are getting interleaved, and the interleaver is designed such that most important bits are retained, okay. And what will happen for n is equal to 64? Interleaver will split the data into 2 streams of length 32 and separately interleave them. Fine, okay. So this is the sub-block interleaver. That's how it works. You have to, this is directly from the standard, okay. No more insight about this, and that's how it is. Only insight is that it retains the most important bit of the polar encoder, that's all, okay. I hope I have made this clear, okay, that this is the key aspect, and that's, so one p of I is given to us, and if you have to generate, if you have to interleave higher number of bits, you generate j of n from p of I, that's all, okay, fine. So this is very dry, okay, that we have to interleave, okay. So what we have done now, let's okay, I came back. So what we have seen till now, DCI, you have interleaved, and how many bits you have? N, correct, okay, right. Here you will see that things will start becoming interesting, okay. And what is this rate matching? As I said earlier and just now, that you have to match the rate which is coming here to the rate which is demanded by the user, and there are certain subtle differences between this rate matching and the PDCCH rate matching, okay. So we'll see that, okay, and as a part of that we'll understand few other key ideas also, okay. So now if you recall, how many segmented PDCCH blocks are there in this case, okay. There is only one block, right, okay, that is what we have seen, okay, that is what we saw, that we gave this number in the beginning, that C will always be 1 for PDCCH chain, okay, right. So now I'll have to recall, we'll have to recall this, I'll have to like remind you about these core sets. What are those core sets? Core sets are those resources, control resource set, on which finally this QAM modulated symbols are going to be transmitted, okay, and they are designed in a special way, okay. We looked at certain part, okay, we are going to discuss that in great detail, okay, but for this slide what is required here is that these are the control resources on which this 4 QAM PDCCH symbols will be transmitted, okay, and they are designed such that the total number of PDCCH bits G, okay, which can be transmitted, this is something like this. We'll come to it, okay. What am I saying here? Here, okay, these core sets are designed, okay, such that you can only transmit one of these 5 number of bits, okay. And what is it telling you? Okay, 108, 216, how are these numbers coming? I will come to it, okay. But what is it telling? That you can only transmit 54 symbols, 216 by 2, okay, 108 symbols, because it's QPSK, okay, right. So there is certain granularity which is associated with core sets, okay. It will allow you to transmit only these many bits, that is all, okay. And what is this telling? Okay, so if it is you are allowed to transmit 108 bits, which means that you are transmitting at a higher rate. So you are allowed to transmit larger number of bits, which essentially means that it's a lower rate because you are giving more resources, okay, correct. Just one example, how many bits maximum if you look at it, okay, we'll look at these examples again, but 164, maximum payload is 164, correct, okay. So at least you will need 216 bits to transmit that, because you cannot transmit them using 108, that's the maximum, okay. So starting from 216 to 1728, okay, right, 164 by 216 is basically high rate, 164 by 1728 is a lower rate, correct, okay. So it is of course the function, how many the core sets are allocated to a user is a function of what SNR it is observing, right, we understand that, okay, because that's the example we took. For the same number of 164 bit, one of these 4 core set size could be allocated to a user, okay, right. So this is denoted as G, okay. So number of bits which can be transmitted for PDCCH block, just to keep the notation same, E is equal to G by C, and what will happen, E will be equal to G, right, because what is happening, C is 1. So the same notation, that how many bits per code block are allowed if G is this, you divide them equally along the number of code blocks, okay. Here C is 1, so you get E as G, fine. E is per code block and G is the total number of bits, correct, okay. So that's how it works, and this please keep this notation in mind, E, G and C is 1, okay. This is associated with core set, and why am I teaching you? Because of course rate matching will depend on what is the size of G, right, okay, fine. So that's how it works. So polar encoder length N, as I just said, can be greater or less than E, correct, okay. 164 I said it is greater than 108 but less than other. So one example, right, okay. So and that's N can be greater or less than E. So what do you need? It requires rate matching, correct, okay. You are generating N bits, but you are allowed to transmit only these many bits, okay, right. So by the way, N is basically the output of the rate match, output of the polar encoder, okay, right. So polar encoder length can be greater or less than E, okay. So let's see, before we go into rate matching, okay, how is this n calculated? Okay, that's what we have to see, and from there it will become clear how rate matching is functioning. Okay, so that's what I'm going to teach you in this next slide. Okay, how basically this n is calculated. Okay, so and there's a formula. Okay, we'll dissect this complete formula. Okay, if formula is this, what are we calculating? N. What is this n? What is the relationship between n and capital N? Capital N is equal to 2 power this small n. So if we calculate this small n, you know capital N. Okay, this is the formula. Don't get carried away by this formula. I'm going to explain this in great detail. Okay, right. So what is happening here? So let's try to discuss this formula in steps by first assuming that n1 is not there. Okay, right? N1 doesn't exist. Okay, so what are we doing here? I'm only looking at, I'm saying n is equal to max min. The formula reduces to this if n1 is not there. We'll come back to n1 also. Okay, so what happens here? What are these different terms? That's what we have to understand. N max and n min, we remember what is that? N min is the minimum polar encoder length in the downlink. N max is the maximum polar encoder length. Okay, we remember what were those values? Okay, so this is, if DCI length is 140 bit, K becomes 164. Okay, for downlink, what is n min? 5. Okay, so minimum n is 32, maximum n is, capital N is 512, right? Okay, so with this, let's see what is happening. So we'll substitute it over here. Okay, input length is K, right? And as I said, polar encoder rate, this is a mother code rate for the polar encoder. What was it? R is 1 by 8. Correct? So this is capital R. Everything is going to play a role here. That's what I'm going to show you. Okay. So what is this? What is N2? There is N2 sitting over here. How is this N2? Okay, what is it deciding? Okay, let's look at this. What is the value here? Log 2 K by R. This is the formula which is given to us. We have to understand what this is so that things become clear here. Okay, right? So what is this? Log 2 K by R, and what is R? R is 1 by 8 rate. Okay, correct? Just hang on with this. Okay, things will become clear. Log of 2 8K. Okay, what is this saying? It decides the code rate. Let's see that how. Okay, so what is it saying? Okay, 2 power n2. If you look at it, okay, if n2 is this, what will it become? Okay, 2 power n2 is the smallest power of 2 which is larger than 8K. How will you read this? If you look at this and you read this, does it make sense? What are we saying here? Okay, right? 2 power n2 is the smallest power of 2 which is larger than 8K. I hope I have, so what is this? Okay, if we look at this formula, it will become clear. Okay, and then take this example. What is this? K is 164, correct? Okay, and if I substitute K over here, that's the number I get. What are we doing? This is the seal, correct? Okay, and what are we saying here? What will it give me if you take the log of 2? It will give me the highest number, okay, highest smallest number which is larger than 8K, right? Okay, so see this, okay, what is happening? Okay, if you take the log of this, okay, you get 11, okay, right? Log 2 of 1312 will give you 11. And what is happening? Okay, what is 2 power 11? 20. So this is 2 power 11 is how much? 2048, right? Okay, what is this? What are we saying here? Now you see this 2 power n2 is the smallest power of 2. n2 you are getting as 11, the smallest power of 2 which is larger than 8K. What is 8K? 1312. Do we get this? Okay. What are we saying here? If it is 10, you will get 1024. Doesn't hold. That's why you are sealing it. Okay. So n2, 2 power n2 is the smallest power of 2 which is larger than 8K. That's what is happening over here. Okay. So what are we saying here? Okay. That if the input is 164, okay, we would like to code it with n is equal to 2048 bit. Why? Because we want the code rate to be low, 1 by 8, at least 1 by 8 or lower than that. See, there are restrictions on the value of n. Okay, n can take values only as 2 power, right? Okay, so if it is 2 power 11, you get 2048. You get, if it is 2 power 10, you will get 1024. Okay, but what will happen if it is 1024? It is smaller than 8K, which essentially means the rate is higher than 8K. Correct? Okay. So now, okay, so what are we doing for, just for example, okay, so we make things simple for us, okay, 164, if you have to simply encode this, correct, okay, let's write it like this, if I have to simply encode this, what will happen here, 164, if its rate is 1 by 8, okay, I will get some certain number of bits between 1024, what is it, 164 into 8, let's do this calculation. Right, that's what it's, okay. Of course, 8K, 1312, okay. You would like to encode, the polar encoder output should be how much in order to have the rate of 1 by 8? It should have 1312, correct? If K is 164, then N should actually be 1312, so that rate becomes 1 by 8, correct? Okay. Polar encoder doesn't allow you to do that. What does it allow? It only allows coding in the rate, how does it allow? Power 2 power n, right? Okay, so what are we finding here? We are trying to find out a larger number than 1312, which will give us a rate either 1 by 8 or lower than that, correct? Okay, right? So, and the number comes out to be 2048, fine. So the maximum is how much? That's what we gave. For the downlink, what is the maximum length polar encoder? It comes, n max is 9, so you are allowed only 512 bits, not 2048. That's why this is coming over here. You see this, okay? So what happens here? Now you see this formula, okay? Does it make sense or not? Okay, n max is 9. What are you getting here? N2 is coming out to be 11, okay? But you are not allowed to. That's why it is coming out minimum of N2 comma N max, okay, right? If N2 comes out to be more than N max, which polar encoder doesn't allow, right? Okay, that's why it is coming out to a minimum of this, right? And you see this, so N comes out to be 9. N min doesn't play a role because it's, of course, it's greater than N min, right? N min is 5, right? If the rate, if N min, if this value goes below N min, then N min, this is a lower limit, right? If this formula gives you, let's say, just for example, 20, okay, right? And then it will become 20 comma N min is 32, so minimum length is 32. That's how it is. Did we get the feeling of it? What is happening here? Okay, it is, so what is it deciding? Okay, it calculates the maximum rate, okay, such that it is close to 1 by 8, okay, right? If that 1 by 8 is lesser than n max, you are fine. If it is more than n max, then it is basically sealed to n max, okay? That's what is happening, okay? Now what happens, okay? So this is basically this operation, this N2, what am I saying here? It decides the code rate. Code rate is decided now. What is the code rate? 168 by 512, correct? Okay, right? That's this formula, this one is deciding the code rate. N2 decides the code rate, okay? Now what is N1? N1 is basically this. This is seal of log to the base E, okay? Right, log E. And what is it telling you? N1 is basically a function of how many resources are allocated, okay? Right? And we'll see that, okay? So what is it saying? Same as this, 2 power N1 is the smallest power of 2 which is larger than E, as we just discussed over here, correct? Okay, same thing, whatever I said here, same operation is happening here, log E, okay, to the base 2, correct? Okay. Now let's say if 432 is allocated, correct? A user is allocated a core set of size 432 bits, okay? What will happen here? You do the same operation, log 32 to the base 2. What will you get over here? 9, okay? Why? Because 512 is 9, okay, and it is more than 8 is what? 256, okay? So it is between 256 and 512, so you will get some 8.3 or 8.4 something, okay? And if you seal it, you will get 9, okay? So N1 is coming out to be 9, okay? Now let's see this, what happens here? And you substitute, now you have all the numbers, okay? I brought back N1 also over here, okay? correct? So what are we saying here? Max, min, look at this is the formula now. What is N1? I just calculated 9, correct? What is N2? We calculated here 11, right? And what is, here it is N max, here it is N min. You do all this, minimum of this is 9 and maximum of 5, 9 is 9, okay, right? The context of this will be clear when I do other operation, okay. I'll take another example. Let's say in this case, what is happening? E is 216. Payload remains same, okay. What is, how much is the payload? I'm not changing, see, when I am saying here, when I say here E is 216, I'm not changing this. I'm not changing the K. K will remain as such 164. What am I saying here? In this case, user is allocated only 216 bits. Right? Okay, fine. So E is 216. What will happen to N1? N1 will reduce to 8 because it is less than 256. Correct? Okay. So you will get N1 as 8. Fine. Okay. What will happen to N? N now becomes 8. Okay. And what rate? What will be the polar encoder length now? 256. What is the polar encoder length here? 512. Input length is not changing. That remains as K. Here, what is happening here? What is the difference between this case and this case? Here more number of bits are allocated than in this case. Okay. User is allowed to transmit 432 bits. In this case, user is allowed to transmit only 216 bits. Okay. So what are we saying here? In this case, polar encoder will give out 512 bits. In this case, polar encoder will give out 256 bits. Now, this is a key idea. If a user is allocated lower number of bits, why should polar encoder generate higher number of bits? Right? Okay. Okay. See, the payload is basically not changing. K is always 164. Okay. In this case, core set size is such that you are allowed to transmit 512 bits. In this case, it is allowed to transmit 256 bits. Okay. Or sorry, 216 bits and 432 bits. Okay. So polar encoder will generate only barely sufficient number of bits. Okay, which PDCCH is allowed to transmit, or the core set is allowed to transmit. Okay, right? So that's how it is decided. So what are the two key factors which playing role over here? One is this rate, other one is the number of resources which are allocated to the user. Right? Okay. Now let's look at this again, third final example. If E is 864, okay, user is again allowed to, this user is basically allowed, for this user 864 bits are allowed, right? Okay. We do this exercise again, N1 comes out to be 10. Okay, you substitute it over here, what are you going to get? Minimum of 10, 11, 9, okay, right? Even though user is allowed to transmit higher number of bits, okay, because of the fact that polar encoder can generate only, is allowed to generate only 2 power 9 bits, not 2 power 10, so it again gets sealed to 2 power 9, right? Okay. So, and based on this, okay, you will see that rate matcher plays a role. Okay. What are we saying here with all these examples? Okay, that the polar encoder length is a function of two factors. Okay, one is basically the code rate you have to try to keep it to say, code rate should be as close as possible to 1/8, okay, right? If it doesn't happen, why will it not happen? Because there are certain restrictions which are imposed on the polar encoder length. And what is this? N min is 5 and N max is 9, right? Okay, so that is first factor which is deciding the polar encoder length. Second factor is how many resources are allocated to a user. That also decides the polar encoder length. Okay, the polar, if user is allowed to, for a user only 256 bits are allowed, why should you generate 512 bits? Correct? You should generate only those many bits. Right? In this case, only 216 bits are allowed, so you will generate only 256 bits. In this case, 232 bits are allowed, you will generate only 516 bits. Okay? In this case, even though 864 bits are allowed, right, you are not allowed to generate 1024 bits because the maximum polar encoder length is only 512, right? So, there is a formula. That is how you have to read it, okay. So, I will stop here and we will continue discussing this in the next class, okay. Thank you.